Introduction to Dynamical Systems, Part 4, Analyzing Stability of Fixed Points for a One-Dimensional Case. In Part 3, we already figured out that attractors can help us predict the long-term behavior of the system. And we discovered that there are several kinds of attractors. Also, we learned how to find fixed points. However, not all fixed points are attractors. When will the fixed point be an attractor? When it is stable. What does it mean that the fixed point is stable? Please note that if we set initial conditions exactly at the fixed point, regardless of the stability properties of this point, the dynamical system will remain at this point forever. So there must be some different approach to analyze stability. Well, in fact, stability means that if we set initial conditions not far away from the fixed point, but at some small distance, then the phase trajectory will converge to the fixed point in the long term. If the phase trajectory goes away from the fixed point, it means the fixed point is unstable. We need to figure out how to analyze stability analytically. Before we do this, let us bear in mind that for linear ordinary differential equations, which are autonomous, we can find an exact analytic solution. With this, you might be wondering, how does this information help us if the dynamical system we're interested in is nonlinear? Let us analyze stability of a simple system, relatively simple system which has dimension 1. Consider the general equation describing such a system. It reads x dot is equal to f of x. For visualization purposes, it is convenient to plot the function f of x against x itself. We make an assumption that our function f of x is smooth. We also observe that when the function f of x crosses 0-axis, we have a fixed point. So by solving the equation f of x equal to 0, we find the fixed point, which we denote as x star. At the next step, we expand our function f of x in Taylor series around the fixed point x star. The Taylor expansion reads as follows. We observe that this expansion contains a linear term, which is x minus x star, and some higher order terms, x minus x star squared, x minus x star cube, and etc. We remember that to analyze stability of the fixed point, we need to place our initial conditions at some distance from the fixed point, and this distance should be small. This way, we introduce a small deviation from the fixed point, which we call z, which can mathematically be described as follows. Z is equal to x minus x star, and we impose a condition of smallness on z such that the modulus of x minus x star should be much less than 1. This is a mathematical expression of smallness. At the next stage, we look at the higher order terms in Taylor expansion. And we observe the following. If x minus x star is a quantity much less than 1, suppose it is equal to 0.1, then x minus x star squared will be much less than the small deviation, because 0.1 squared gives us 0.01, and indeed it is much less than 0.1. And the same applies to higher order terms, cubic terms, term fourth order term, and etc. Now, in the Taylor expansion of our function, we can take into account this observation and simply neglect all terms which are nonlinear, all higher order terms, and this allows us to rewrite the Taylor expansion approximately as follows. So we are left only with linear terms. Next, we would like to rewrite the equation describing our dynamical system in terms of the small deviation z, as follows. We take the expression for z and differentiate it with respect to time, and that's what we obtain, and we observe that the time derivative of the fixed point x star dot must be equal by definition of the fixed point. We would also like to express x as a function of z, to be able to substitute this into the original equation for the dynamical system. Next, we combine the expression for f of x as the expression for f as z plus x star, plus the knowledge that x dot is indeed equal to z dot. And we substitute these two expressions into the original equation for the dynamical system. And we obtain the equation at the bottom of the slide. This is still a nonlinear ordinary differential equation, so it is still not exactly solvable in general case. So we need to do something about this equation. We would like to express f of x through its Taylor expansion. We make this substitution, and we can write down a first-order differential equation for z, in which the term f taken at the fixed point must disappear, must vanish, because it satisfies the definition of the fixed point x star. Please note that in using the Taylor expansion, instead of x minus x star, we substitute the value of z, because it is the definition of z. This way, we obtain an expression, an equation, which describes time evolution of a small deviation from the fixed point as long as we stay around the fixed point, as long as the deviation stays small. This equation is obviously linear, because the derivative of the function f at the fixed point is just a number. And therefore, this is what we call a linearized equation. The significance of the quantity f dash at x star is that it represents the slope of the tangent straight line which goes through the fixed point. So that's the geometrical meaning of the constant coefficient in the linearized equation. The linearized equation appears to be a linear ordinary differential equation with a constant coefficient which is exactly solvable. And the solution for this equation reads as follows. Deviation behaves exponentially with time. How exactly does it behave? Well, it depends on the sign of the derivative of f at the fixed point. If this derivative is positive, it means that the deviation grows exponentially with time. What does that mean? The deviation z is in fact the distance between the state of our dynamical system and the fixed point. So if z grows, It means that the state of the dynamical system goes away from the fixed point, which means that the fixed point is unstable. On the contrary, if the derivative of f at x star is negative, it means that z exponentially decays. And this means that the state of the original dynamical system approaches the fixed point, which implies that the fixed point is stable. Now, let us analyze the stability of a one-dimensional system using an example. Our example is going to be a first-order ordinary differential equation describing the population dynamics in the simple case, relatively simple case. There are two parameters in this equation, alpha and c, and alpha has the meaning of the growth rate of the population when it is very small, and c has the meaning of the optimal size of the population, which can be sustained given the resources available. First of all, we need to observe that the right-hand side of this differential equation represents a function of p which is smooth. Smooth means differentiable. Then we need to find fixed points of this equation by setting to 0 the right-hand side f of p. Let us do this. So we set to 0 the product of two terms, alpha p and 1 minus p over c. And it is immediately obvious that we have two solutions to this equation. The first one is p equal to 0, and the second one would satisfy the condition 1 minus p over c equal to 0. So the first fixed point is at 0, as stated before, and the second fixed point can be found from the second equation, and the second equation is solvable, so p2 star appears to be equal to c. So there are two fixed points in the given dynamical system. Now let us analyze stability of these fixed points. To do this, we need to introduce a small deviation from the fixed point. The deviation is denoted as z, and it is a difference, p minus p star, and the condition of smallness reads that the modulus of p minus p star is much less than 1. We can immediately write down a linearized equation for z, which involves the derivative of the function f at the fixed point. Because we have two different fixed points, we will have two different derivatives of the function f corresponding to the fixed points, and there will be two different linearized equations. Let us try to find the derivatives of the function f at the two fixed points. We start from opening the brackets and multiplying alpha p by 1 minus p over c. When we do this, we obtain a second-order polynomial alpha p minus alpha over c times p squared. This function is easy to differentiate. Let's differentiate it and obtain a linear function of p, which reads alpha minus 2 alpha over c times p. Let us try to find the value of this derivative at two different fixed points. First, at 0. Instead of p, we substitute 0, and we discover that the value of the derivative is simply equal to alpha. For the second fixed point, instead of p, we substitute c, and after simple calculations, we discover that the derivative is equal to minus alpha. Let us try to find the geometrical interpretation of these derivatives. Please note that alpha is a positive constant. On the graph f of p as a function of p, it means that the slope of the tangent line to the function f at the first fixed point appears to be a positive number. So and the slope of the tangent line at the second fixed point appears to be a negative number. So if we consider the angles these tangent lines make with horizontal axis, these will be some angles phi1 and phi2, then it means that the tangents of phi1 is plus alpha and tangents of phi2 is minus alpha. Now analyze the stability of the fixed points. Start from the first fixed point at 0. The linearized equation reads z dot is equal to the derivative of f at 0 times z itself. For the derivative, we substitute the value alpha. This linearized equation has the solution, which is equal to k times a certain an exponential function of alpha t. K is a constant which is found from initial conditions, and in principle it can be positive or negative. However, what is really interesting for us is how the modulus of z of t, the modulus of the deviation behaves, because the modulus of deviation will give us the distance from the fixed point. Now, because alpha is positive, it means that the modulus of z will always grow exponentially, whether z is negative or positive. This means that the state P of the dynamical system will go away from the fixed point at 0. It means that the fixed point at 0 is unstable. Now consider the second fixed point, P1 star equal to C. We apply the same procedure. We write down the linearized equation in which the derivative of the function f is substituted and it is equal to minus alpha. So the linearized equation reads like this. We can also solve it, and the solution is another exponential function of time, and again z of t can be positive or negative depending on the value of k, which is found from initial conditions. However, because alpha is positive, minus alpha appears to be negative, and it means that whether z is positive or negative, the modulus of it will be exponentially decaying, converging to 0. And this means that the state P of the dynamical system comes closer and closer to the fixed point as time goes by. This means that the given fixed point is stable. Let us illustrate these stability properties on the phase line diagram of this dynamical system. We observe that when the tangent line has the slope which is positive, which happens at 0 fixed point, such a fixed point is unstable, which means that if we set initial conditions slightly away from the fixed point, which in our example is slightly to the right of 0, we are carried away from the fixed point, and the state P goes away from the fixed point as time goes by. On the other hand, if we consider the second fixed point, P2 star, the slope of the tangent line at this fixed point is negative. This means that the fixed point is stable. This means that if we set initial conditions in our example slightly to the right of the fixed point, as time goes by, the system gradually converges to the fixed point. So this is the geometrical interpretation of stability properties of the fixed point in a one-dimensional case only. I acknowledge the professional and technical assistance from Olga Sosnovtseva, Dmitry Postnov, and the Center for Online and Blended Learning in the University of Copenhagen, Denmark.